Hi everyone, this is Physics 2212 Lab 4 where we're looking at magnet braking. So our objectives is to study the induced current created by the change in magnetic flux as a magnet travels through an aluminum foil roll. So we're basically looking at how the magnetic force of the induced current causes the magnet to flow through the aluminum foil roll slower than if it were flowing through a system where there was no actual conductivity in the aluminum foil roll. So our models are Faraday's law, which gives us the induced current once we divide it by R. And then Biot-Savart's law is what we use to find the magnetic field. And then Newton's second and third laws, specifically looking at gravity and the impact force of gravity and the resulting velocity and position as a result of gravity and our current forces. And then our discoveries is the experimental and computational time that it took for the magnet to go through, and the system is the magnet and the aluminum foil, while the surroundings is everything else. So what was done, basically we were releasing a magnet into a tube of aluminum foil and then measuring the time it took the magnet to get through. I am not going to force you to suffer through my horrible recording of it. So here's a great, beautiful simulation of it. And then air resistance was assumed to not impact the system. The bar magnet was assumed to be a dipole. However, this eventually leads to error because my magnets have seen better days, so they're really, really weak. And then the only forces that were present were the magnetic and gravitational forces based on our assumptions. So the data, as you can see, I have the length, my trials, or the tube dimensions, my magnetic properties, and then the average time was found to be about 0.8 seconds. So here's the code. There's a lot. The initial conditions are on the right side of the screen. So you have the length of the tube and everything. Then you also have the magnet's properties and then the magnetic dipole, which gives us the magnetic field. And then on the left side of the screen is the actual calculation of the magnetic force and then how that eventually contributes to F net. And then finding the bar velocity and position as it updates over time. So here are our findings. We find that in this particular computational system, the time in the tube is about 0.826 seconds, which is awesome considering that my magnets are terrible. As you can see, we start off at the initial velocity of 0, then we are going down, 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 and at one point, this flat line in the middle here is to signify that we are neither accelerating nor decelerating, which means that we have reached equilibrium between the induced current force and the force of gravity before we eventually decelerate again to the bottom of the pipe. So sources of error, like I said, my magnets have seen better days. The magnet dipole moment may no longer exist at this point. I am very frequently dropping my magnets, mostly just by pushing them off the desk. So I'm sorry if that affected it. And then also air resistance still exists, but we are assuming that this is a perfect system rather than including air resistance in our system. So then what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the following magnet change? And our answer is a lower resistivity equals larger induced currents, which gives stronger opposing forces initially, but the nature of the braking charges from dissipative to something much closer to ideal magnetic repulsion, where the conductor holds in the flux and strongly resists any relative motion rather than just slowing it down. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The magnetic braking is drastically decreased by having holes cut into the tube. As a result, the magnet would fall drastically faster, signifying a reduction in the induced current as well.